Welcome back to lesson 2 of week 2. In this lesson, you'll learn how to convert between hexadecimal and binary. I find that students who've learned about hexadecimal still don't necessarily know how to do this type of conversion, which is much easier than it looks. It's actually really easy to convert between hexadecimal and binary because there's a good match between the digits of hexadecimal and the numbers represented by one group of 4 bits. So we'll look at that match and we'll quickly review how to convert hexadecimal to binary and binary to hexadecimal. It's easy to convert binary numbers to hexadecimal numbers and vice versa. That is because each hexadecimal digit exactly matches one 4-bit binary number. When we do the conversion, there are no remainders, no subtractions, or anything like what we've had to do in converting to decimal. This table shows the exact match between binary and hexadecimal, but you don't have to memorize this. If you're absolutely stuck in the exam, you could write this out in a couple of seconds. It's just counting from 0 to 15 in binary and counting from 0 to 15 in hexadecimal. And once we have that match in our minds, every single conversion is super easy. We just write the equivalent binary number under each hexadecimal digit, and that's it. The number works. We don't have to convert it to decimal. We don't have to know what the decimal value is. We just write the 4-bit binary number under each hexadecimal digit. So let's look at a couple of examples. So let's look at an example. If we had to turn the hexadecimal number 32 into binary, 3 is 0011 in binary, 2 is 0010 in binary, so we put those together, 0011, 0010. We don't have to work out the decimal value of any of these numbers. The conversion just takes care of itself. Here's another example. What if we wanted to convert the hexadecimal number F2 into binary? Well, F, that's actually 15 in hexadecimal, and in binary it's 1111. 2, we've already looked at, 0010. So F2 is those two binary digits put together, 1111 0010. And that's it. And finally, if we had to convert the hexadecimal number AB into binary, looking on our table, A is 1010, B is 1011, so the whole thing is 1010, 1011. I've no idea what that number is in hexadecimal, and I don't need to know. That's the answer. And similarly, if we convert binary to hexadecimal, we can split the binary number into groups of 4 bits, and under each group of 4 bits write the equivalent hexadecimal digit, and that's it. Once again, we don't have to know the decimal value of the binary number. So here's a worked example, 1000 0100. 1000 is 8, 0100 is 4, so in hexadecimal it's 84. Notice that's not decimal number 84, it's a hexadecimal number. You can work out what it stands for if you want to. Here's another example. The first group of bytes stands for 6, and the second group of bytes is equivalent to the hexadecimal number B. It's actually 11 in decimal. And so that group of bits represents the hexadecimal number 6B. So here's our final worked example, a number in binary. The first group of 4 bits is equivalent to D. The second group of 4 bits is equivalent to A. And so the whole thing is DA. I don't know what those numbers are in decimal, but they are the same number. And that's all you need to do in the exam. So occasionally in the exam, they might give you a much larger number to convert between hexadecimal and binary or vice versa. Don't panic if this happens. Just use the principles that we've learned. Convert the hexadecimal digits one at a time into groups of 4 bits, or the other way round, group the bits into groups of 4 and convert each group of 4 into hexadecimal. You don't need to know what the number represents. So here's an example that's much bigger than anything I've ever seen in any exam. But let's say they asked you to convert the hexadecimal number ABB76CF0. That's a massive number. We'd just write all those digits down, one after the other, and under each one we write the equivalent group of 4 bits, also called a nibble. And that's it, we've solved the problem. ASCII and Unicode are often represented using hexadecimal digits. So here are the text characters from A to H in lowercase. They're decimal, binary and hexadecimal values. You don't need to memorize this, but I just thought that might be interesting to you. And color codes are also represented frequently in software using hexadecimal codes, and you can find out more about that by browsing online, but again, you don't have to memorize any of this for the exam. So to recap, if you need to convert between hexadecimal and binary, create the table of the 15 digits, 16 digits if you need to. You convert each hexadecimal digit into a group of 4 bits, or convert groups of 4 bits into their equivalent hexadecimal digits. That's literally all you need to do, and you don't need to convert any of those values into decimal. So I'm setting you a simple programming challenge to create a Python program to convert between hexadecimal and binary, and in the next of these lessons we'll look at how we represent negative numbers in binary.